distinguished guests, colleagues, students. I'm Professor Guangyu Zhu, head of Department of Chemistry at City University of Hong Kong, and the facilitator of today's lecture. It is my pleasure to welcome you all to today's CTU HK distinguished lecture. We are very pleased to welcome Professor Zuowei, Chair Professor in the Department of Chemistry at Southern University of Science and Technology, SUSTech, Shenzhen, China. Professor Xie received his bachelor degree from Hangzhou University, now Zhejiang University, in 1983. His master's degree from Shanghai Institute of Organic Chemistry, Chinese Academy of Sciences, in 1986, and his PhD in 1990 through a joint program between the Shanghai Institute of Organic Chemistry and the Technical University Berlin. He joined the Chinese University of Hong Kong in 1995 and was promoted to chair professor in 2006. In 2022, he moved to SUSTech as chair professor. So Professor Xie is a distinguished member of the Chinese Academy of Sciences and a fellow of the Royal Society of Chemistry and also Chinese Chemical Society. He is a leading expert in carborane chemistry. His pioneer work focuses on the Regio and Enantio-selective activation of cage boron-hydrogen bonds, opening new avenues for the functionalization of carboranes with important applications such as catalysis and medicine. He has received numerous prestigious awards, including the Humboldt Research Award in 2022, the Hong Kong RGC Senior Research Fellowship 2020, the State Natural Science Prize in 2008, and the Croucher Award in 2003. Today's lecture, titled Unlocking Carborane Potential, Regio and the Enantio-selective boron-hydrogen activation methods, Professor Zhao will share his insight with us. So please join me in welcoming Professor Xie to the stage first. And on behalf of CTU HK, I'm delighted to present you with a portable tea set. Now, this set, adorned with the CTU HK logo and also a floral emblem, symbolizes the elegance of Chinese culture and our shared commitment to excellence. So please accept this gift as a token of our appreciation. We hope you enjoy it. So now let's invite Professor Xie to deliver his seminar. Professor Xie, please.
Thank you very much, Professor Zhu, for a very kind introduction and also for this gift. Yeah, good afternoon, ladies and gentlemen, colleagues, fellow students. Yeah, it is my great honor to be invited to deliver the distinguished lecture here at the CTU. So I have seen many my old friends, and I'm happy to visit CTU again. So I also like to thank the selection committee for giving me this excellent opportunity. Yeah. To visit CTU again and then to see many of my old friends here. And of course, I also like to thank Zhenping for the arrangement of my trip here, and also my visiting schedules here as well. Yeah. So today I'd like to share with you some of our recent work in the functionalization of carboranes. Okay, some of you might know the carborane, or some of you might not. So today my focus will focus on this molecule. Right now it's spinning around. So this is a three-dimensional molecule. Three-dimensional molecule with icosahedron geometry. So it contains 2 carbon, 10 boron, and 12 hydrogens. This can be viewed as a 3-dimensional analog of benzene. So I believe that all you know benzene. This is a very unique and famous organic molecules, right? It's two-dimensional. The benzene itself has a very limited uses, usually used as an organic solvent in organic chemistry, right? However, the derivatives of benzene are finding many applications in materials, in medicine, and in many other areas. So likewise, carborane as well, because as an analog, three-dimensional analog of benzene, the carborane itself has, again, limited applications. However, the functional carboranes have been finding many applications across different areas. For example, in the materials, okay, in the imaging, as an imaging material, as a nano vehicle, optical material, as well as in medicine as a boron neutron drug. However, you can see if you want to make this carborane more powerful, derivatization is very important, and then there's a must process. Otherwise, you will not find more applications with these molecules. So in order to functionalize these cluster molecules, we are facing three challenging issues. As listed here, we have chemoselectivity, we have regioselectivity, and we have enantio-selectivity issues. Okay? We have to solve these issues, otherwise the functionalization will not be selective. Then means you will get a mixture of product, then might be a useless materials. Okay? So to do so, we have developed a strategy for the selective functionalization of clusters, and I hope probably in the next about 40 minutes, I will show you our methods for the selective functionalization of these cluster molecules by giving a few examples. So first of all, let's look at the chemoselectivity, because this molecule has, 2 Kj carbons and 10 boron atoms. How do we selectively functionize, for example, the carbon vertex and the boron vertex remain intact? So let's look at the orbital diagram of these clusters. Each Kj atom here, regardless of carbon or boron, adopts sp hybridization. Okay, so one of the sp orbital, in fact, is sigma bonded to the external hydrogens. Right, other sp orbital is point to the center of the cluster, forming the additional so-called bonding orbitals. So that's kind of cluster can be stabilized. So if you here agree with me, if this is a sp hybridized orbital, so this proton will be acidic proton. So as showing here, this is acidic proton, and the BH is hydratic. Why? Now you can see their electronegativities is showing here. Carbon is greater than hydrogen, then greater than boron. In other words, the BH and the CH, the polarity is very different. So the BH hydrogen bear a partially negative charge, and CH, this hydrogen bear a partially positive charge, so that you can easily realize the distinction between CH and BH vertex is not so difficult, because by using a strong base, you can remove the acidic proton, and the basic proton, the BH, will remain intact. So for example, we start with these molecules, these model molecules. We can use strong base to remove both CH protons and generate the double bond there, and thus we give a name called carboride. Okay? Now this double bond can be bonded to the transition metal to form metallar carboride. And this carboride is an intermediate. It cannot be isolated. However, the corresponding metal carboride, this can be isolated and well characterized. And then the chemical properties is depend on the electronic configurations of the metal. So different metal will have a different properties of metal carborides, so that we can modify the K carbon or boron positions with different substituents. Or we can modify both K carbons using a different substituents, leading to a family of the functionized carboranes. So I will not go to detail, as this already summarized in this basic in this accounts paper. All right. So after addressing this chemoselectivity issue, this is relatively easier to realize. Now, what about the second challenge showing here, Regio selectivity? See, there are 10 BH vortex. How do we distinguish each of them, or some of them? Of course, this molecule has a certain symmetry, right? So that these 10 can be divided into, can divide it into 4 groups, right? Okay? In other words, we have to distinguish this group of BH. All right, before we started our research in about 2012, what has been done in this field, right? So as I have mentioned earlier in the first slide, this is a 3-dimensional analog of benzenes. So this is aromatic species, all electron delocalized through the 2-electron 3-cent bonds. Now, aromatic molecules, can undergo electrophilic substituent reactions, right, to give a substituted carborane. However, the degree of substitution is hardly to be controlled. In other words, the N here could be from 1 to 8, okay? So in principle, you will get a mixture of the product, and then they can be separated as the polarity difference is quite small. So unless you get a single product, otherwise such a reaction is not so useful. The second method, you remove one of the vertex, and then to open up the cage, and then you do the capping reaction to install another vertex. So in this case, you might be able to install the substituent to the position number 3 only, right? In other words, number 3 is bonded to both K carbons. So this is an indirect method. You have to remove one of the vertex and then recapping, right? So this is the indirect method, and then the reaction scope is highly limited. So the other functional method is known as transition metal catalysis. Now, in case you can do the electrophilic substitution reaction, for example, allow you to install a single iodine into one of these boron, and then you can do cross-coupling reaction, converted the I into the other substituents. Those are the known methods before we started our work. You can see from these known methods, either the substitution degree can hardly be controlled, or you use a complicated indirect methods. Otherwise, the functionalization or selective functionalization of the cluster is impossible. So what do we do on the basis of our own work as well as others in the field? Then we come up with a general strategy for the selective functionalization of BH bond with transition metal catalysis. So this strategy consists of 3 principles. So principle number 1, I try to give a little bit more explanation here. For this, the 1, 2, 3, 4, all the way to 12, this is IUPAC numbering systems for the cluster. So the 2 black dots are the K-j carbon. Those open circles represent the K-j boron. All right, for the 3 and 6, those 2 bolons, they are bonded to both K-j carbons at the same time. Since the electronegativity of boron is smaller than the carbon, so in other words, here the K-j carbon serve as an electron-withdrawn group to pull those electrons on the boron towards the K-j carbon. So both B3 and 6, those 2 positions, the boron are highly electron deficient. The corresponding BH bond, highly electron deficient. So can be selectively activated by electron-rich metals. So if we use the electron-rich metal catalyst, we are able to selectively activate both BH. So this is the rule number 1. So rule number 2, let's look at those 4 atoms. They are far away from the K-j carbon, or they do not have any bondings with the K-j carbon, okay? So they are relatively electron-rich because they do not bond to the K-j carbon. So relatively electron-rich BH bond can be activated selectively by electron-deficient metal catalyst. So if we use electron-deficient metal catalyst, in other words, we use electrophilic metal center, or selectively activate relatively electron-rich, this 4 BH bond. Now what about the B4, 5, 7, 11? So their electron density is lying between the electron poor and the electron rich groups. It is very hard for the metal itself to selectively activate the BH bond of this group. So what do we need? We need the help of the directing group. So with the assistance of the directing group, we're able to activate the BH bond in this group so that we can achieve the selective functionalization of clusters by combining the electron density of the cage atoms as well as the properties of the catalyst. There's a match. As long as the properties are matched, and then we can do the selectivity. So our groups, as well as the groups from around the world, we work together, have developed a toolbox for the selective functionalization of this cluster based on our these principles. Okay, so some of the major players are listed here. Okay, but by no means this is extension. Right now, I've seen that more research groups are joining this effort. So we have summarized again our the work on this subject in this recent account. And I hope I will give you a few examples and then to see, based on this principle, how do we develop the methods. So the first method we develop based on these principles is tetrafluorination of these clusters, catalyzed by electron deficient palladium-2 catalyst. In this case, again, we want to activate relatively electron rich this A9 and then 10 and 12 vortex. So we use electron deficient catalyst here, the palladium-2. The mechanism I'm showing here, the palladium-2 attacks the most electron-rich BH bond and then generated the metal boron bond, right? And this bond, the metal, here metal is in the oxidation state of 2. Then we use a strong oxidant, fluoride cation, to oxidize the palladium-2 to palladium-4. Why? Because that can promote the reductive elimination, facilitating the formation of the BF bond, release the catalyst. And the catalyst will enter the second cycle. And after repeating 3 times, we are able to selectively prepare the tetrafluorinated species. So this appears to be the first catalytic selective functionalization of clusters in this field. Now, if you ask why only these 4, this reaction will not go further, because this group, let's go back. Yeah, this group, right? They are relatively electron rich. And then there's a difference, the difference in electron charge between the 3 groups, okay? Unless we heat it up to a high temperature, otherwise reaction will stop here. Now you will say, why not just stop at 1 or 2? Because the difference in charge density among the 4 atoms is very small, okay? It cannot be stopped at 1 or 2 or 3, all right? So this is one example. The second example, can we selectively functionalize one of these 4 atoms? The answer is yes, but we need the help of this directing group. The directing group here is the amide group, okay? And for example, we're able to selectively functionalize the B8 positions by using similar catalyst, palladium-2, and use the aryl iodide as a coupling partner. At the beginning, we thought, yeah, this reaction will proceed as we expected. It's very simple, straightforward. In fact, after mechanistic studies, then we change our view on the reaction mechanism. In other words, the original proposal is incorrect. The correct reaction mechanism through a mechanistic studies, while labeling study or the isolation of the key intermediate. The first step is the metal activate the B4 bond here, right? Not B8. Then after the oxidative addition reaction, the formal oxidation state of palladium is changed from 2 to 4. At the same time, the metal will migrate from 4 to 8. And then followed by the reductive elimination. Why the metal want to migrate from 4 to 8? That's because of thermodynamic reasons. This intermediate is more stable than the one thermodynamically. So the metal will move from one position to the other position. How do we know? Because we label the palladium here, label this deuterium in this position, and this deuterium will migrate from 8 to 4. The metal will move from 4 to 8. Okay? So after this detailed magnetic study, we were able to come up a so-called new proposal, casual working mechanism. But this, after discovery of this new mechanism, we develop another set of methods based on these findings. So what about the more electron deficient 3 and 6 position? In this case, we need to use electron-rich metal. Here we use iridium-1. Iridium-1 is a very electron-rich catalyst. Okay, so we're able to functionize both 3 and 6 position. You know the B-pen can be easily converted to other substituents through a conventional transition metal catalysis methods. So the mechanism I'm showing here, a little bit more complicated. After the magnetic study, we propose there's a cycle from iridium-1, iridium-3, 5, 3, and 1. Okay, and this was later supported by theoretical calculations. So now the third example will show you how to activate this the middle group BH bond. We need the help from the directing group. Here is a carboxylic acid. Okay, we use again here is iridium-3 as a catalyst. Now iridium-2, iridium-3. This is more electron deficient. So we're able to install those substituents onto the B4 very selectively, right? 100%. And this configuration of the double bond, again here the cis configuration, as this is the cis addition. Now, what is the reaction mechanism? Again, we able to isolate the key intermediate, okay? This is the key intermediate. And then which is characterized by single crystal X-ray analysis. And this is the 18 electron species. You know the 18 electron species is stable, right? Otherwise, we are not able to isolate it. So in order to make it 18 electron species, we need a DMSO. We use a DMSO, a coordinating ligand, to saturate the coordination sphere of the metal so that we can isolate this reactive species. And then based on the control experiment, we come up these mechanisms. So first of all, the carboxylic acid will bring metal close enough to only one of the BH bonds. Okay, so this BH then activated by the metal to form the metal boron bond. So the insertion, protonation, and the decarboxylation reactions. So this carboxylic acid group we call as a traceless directing group because it induces here in order to make excellent selectivity. After reaction, this will departure from the substrate. So allow you to do the further functionalization because we have a CH, right? So we can use our previously developed method to introduce another substituent into the cage. So I always told my students, magnetic study, understanding is extremely important to develop the new methods. Although it took my student a whole year to get these crystals and to get the understanding of the mechanism. So why is so important? You see, we believe this will be a transition state, right? Carboxylic acid group bring the metal right close enough to one of the BH to form the so-called, this is 6-member ring transition state. So that only this BH bond will be activated, leading to the formation of the 5-member ring with a metal boron bond. We know that metal boron bond is quite reactive towards many substrates, not only one alkynes. So if you understand that, so based on this intermediate, then we have developed a set of the methods for the further functionalization of this cluster. So this single intermediate, in fact, will leading to over a dozens of methods. only of selected examples are showing here. We're now able to do almost all kinds of functionalizations with the different substituents. Okay, so that's why the magnetic state understanding is a key for the development of synthetic methods. All right, I hope through these few examples, you agreed with me that we're able to do the Regio selective functionalization of these clusters. So what about the other issues in Enantio-selective functionalizations? Enantio-selective functionalization can only be achieved if we can adjust the Regio selectivity. Otherwise, you will get a bunch of steric isomers, and then they are impossible to be separated in general sense. All right. So when we talk about the enantio-selectivity, and then we have to talk about the chirality. And the chirality is a very important concept in organic synthesis, right? And of course, in the life science, right? Amino acids are all chiral amino acids. There are 4 types of chiralities. In general, I will say here. Okay, central chirality, planar, axial, and helical chiralities. So now I want to introduce a new chirality we call as a cage chirality. All right. Just by looking at this, you don't see, the chirality like those, the reported one, right? This cluster like a Bohr molecule, how do we have such a chirality? So again, before we started our work, what has been done in the field? We will not say we are the very first one. Always something has been done if you go to the literature to find something. What has been done? So in the literature, they have a couple of reports about the chiral resolution of these clusters. This idea actually borrowed from organic chemistry, right? Organic chemistry, you can separate the stereoisomers by chiral column separations or by other ways. In this case, use a chiral column, it is possible to separate those enantiomers, okay? Or the other report, like here, these papers report the chiral carborane derivatives with the chiral center and the carbon, not the cage, right? Because you can see these are the chiral center outside the cage. So that is not a chiral at cage molecules. And these are chiral at cage molecules. These are not chiral at cage. Because the chiral center is out of the cluster. In this molecule, carborane serves as a substituent only. Just is a very special bulky substituent, right? So that has been done. And then we ask ourselves, it is possible to develop so-called asymmetric catalysis to prepare only one of the enantiomers, okay, through a chemical means, not through a chiral separation, right? Because we have been able to do the chemistry Regio selectively. How do we do that? So our method we call a desymmetrizations, right? For example, now this is a cluster. You have one cage. This is a cage. Cage is a substituent cluster. If we can introduce a second cluster, a second substituent onto the cluster, what means? As a result, the symmetry of this molecule will be lowered, right? you introduce more and more substituents. So the symmetry will be broken down, so that then you will have, think about it, mirror image molecules. So just like your right hand and left hand, they are mirror image. They are a pair enantiomers. They are not the same, right? Well, your right hand, your left hand, it cannot overlap completely. So that we call a pair or mirror image. And here, yeah, showing you a pair of mirror image. And if the substituent goes to the B4 position, we call this is R configuration. If this goes to B5 position, there will be S configuration. They are a pair of enantiomers. So in the previous result, I show you the Regio selective functionalization. We always get a racemic mixture, two stereoisomers. So can we get only one of them? In principle, it's yes. Okay. Before that, I will introduce you how do we define this B4 substituent as a R configuration, B5 as S. So we come up definitions. This is our definition, and it is now accepted by the community. Of course, this need to be further refined. How do we do that? Let's take the cage substituent. Let's take the cage substituent 1 as an example, right? The number of cage carbons 1, 2, and 9, and 12. There's a mirror plane here, right? There's a mirror plane. So the 3, 6, 4, 5, he shows 3, 6, 4, 5, 7, 11, 8, 10. They are a pair of enantiomers, right? Now, go on. Okay, if we take the up pentagon, okay, start, you look it down from the top, and you start with 2. The substituent on the 4 and then 3 position, that's called R configuration because it's clockwise. On the other side, 5 and 6, this is the S configuration. It's anti-clockwise or counterclockwise. So same is true for the bottom pentagonal belt. So with this definition, and then you can define which one substituent is S, which substituent is R. How do we know? We use absolute structure to define. All right? With this background, and now we're able to introduce, so our methods, how do we do that? We have to introduce a chiral ligand here, because chiral ligand can create a chiral environment for the catalyst metal center. So if this is a chiral environment, so maybe this B4H will be selectively activated, or maybe B5 will be selectively activated, so leading to the formation of the single enantiomeric product. Okay, so this is the key for the introduction of the chiral ligand, and this type of chemistry is well known in organic synthesis, in the carbon-based molecules. And now we're able to extend it, this carbon-based, two-dimensional, to such a three-dimensional cluster molecules. So let me give you the first example I will show you. That is the intramolecular coupling reactions. So this reactions, right, looks simple. We use this as a model substrate reactions, and then we have to, examine different chiral ligands. Which ligand will give us an ideal product? We don't know, okay? We always try and error. We have to test all the chiral ligand available. At the end, we find this one. Yeah, this one, R1, is a very good ligand for this asymmetric catalysis, giving the product in 98% yield and 90% EE. Though it's not perfect, but this is very good already. And this is the first example in the synthesis of chiral at cage clusters. Now, you might say, what about AI? AI might help. Yes, I was pretty positive in this side. If we have enough data and tell it's AI might propose a sort of chiral ligand for these particular reactions, so that it will save us a lot of time and a lot of manpower, a lot of money as well. So that's probably AI can help. I'll just show you the substrate scope. You see, this is the absolute structure, all right? And tell us, yes, this is the ACE configuration. And we also do the CD spectra, right? It's showing you, okay, this is R and S is a pair of image, right? You see, there's a highly symmetrical CD spectra. And because with absolute configuration of the molecule, we know which one is S, which one is R, right? So what about the reaction mechanism? Again, we always ask ourselves, how does the reaction process? Why the L1 ligand is so good? Is there any special reasons? All right, this is a general catalytic cycle, and we know from A to B, this step is an Enantio-selectivity determining step, because the BH will be activated to form the metal boron bond, and the substituent will goes to these positions. All right? Now, why? There's two transition states, S and R. Why this configuration is favored? Now, we use the DLT computation method to determine the transition state. This is a transition state, S configuration, R configuration. As you can see from this structure, in the R configuration, there's a steric effect between the ligand as well as the substrate. So this steric effect will enhance or increase the energy level of the transition state. The difference is about about 2 kilocalories per mole. It translated into about 90% EE. So based on these magnetic studies, we now can understand why the reaction proceeds well with particular chiral ligand. Now, can you do something more complicated? This is the intramolecular. Can you do intermolecular? The answer is yes. We're able to do these reactions, okay? Again, with perfect, in this case, with perfect EE and a perfect yield. Again, we have to screening all kinds of chiral ligand available in hand, because we don't know which one will work well. So after the screening, we find this chiral ligand, L8, works perfectly for these reactions. And then we can further tune the reaction conditions. You can see now with almost perfect result, 99% EE and then 99% yield. This is the absolute structure of the different enantiomers. And here is the CD spectra. It's perfect. There's a mirror image, right? Again, we use S configuration ligand, we get S product. We use R configuration ligand, we get R product. All right? So this is the substrate scope, the alkynes. We can do control experiment. Some more detailed results are showing here. For example, first one, we run the deuterium experiment. and then to confirm the D, the deuterium, the hydrogen from the cage, BH, okay? Because in the absence of other deuterium source, the 95% of the D is migrate of coming from this cage. And then we also measure the KIE is around 1, indicating that the BH activation is not involved in the rate determining step. And then we propose a possible reaction mechanisms. And then we again use DLT to understand why one transition state has a lower energy than the others. That in this case, there's no stereo effect. That's what we call a non-covalent interactions, because in the S configuration, there are more CH pi interaction, so that the energy making the energy of the S transition state is lower than the R configuration by about 4 kilocal per mole. So that translated into about almost 100% EE, okay? So another method I want to share with you is migrations. So a number of years ago, we have published this result in Angevandate. The metal will first of all undergo oxidative addition reactions, and then insertion, followed by the migration. The metal will be migrated from the carbon to the cage boron, okay? And then reductive elimination, so that we can do the multiple functionalization in one step. And then after we're able to do the Enantio-selective functionalization of the cluster, and we ask ourselves, can we convert this unsymmetrical reaction into an asymmetric version by adding the chiral catalyst? The answer is yes. So in the previous two examples, so the transition state is showing here. And now, for example, we added the chiral ligand, will create a chiral environment, making the metal selectively migrate to the cage BH. Okay? So this is a principle. In fact, it's work well again after the screening of the ligand. We're able to find this ligand, the bis-amide ligand. This ligand works very well for these reactions. So we have the absolute structure. Again, we have CD spectra. And then we have expanded the substrate scope. We also can do the scale-up reactions, the gram scale. We can do further transformation. For example, we'll just use the one-part reaction and to functionize the both cage atoms. And we can also cut off this double bond to make a ketone. Of course, ketone can do the further functionalization. So think about, look at this iodo. Iodo is a very good functional group. It can be converted into many other substrates. Here is R. So what about into the phosphines? We know the chylphosphine is a larger family of chiroligand for asymmetric catalysis. So by simply converting the iodo into the phosphine, we will generate a new class of phosphine based on the chiroligand, right? This class ligand. Originally, we thought this might be difficult. So even more than a year ago, I put a question mark there. Now, I can tell you that we're able to complete this reaction. We have generated a class of new type of chirophosphine ligand for asymmetric catalysis by just converting the iodo into a different phosphine species. So what about the reaction mechanism? There are two phosphine centers here could bond it to the metal. So first of all, we want to know if both really bonded to the metal. So we prepare a new ligand with only one phosphine unit here. The results showing that, the basic results are almost identical. In terms of the yield and the EE, suggesting that only one phosphine is active, the other one is useless. So that we propose a catalytic cycle. Here, only one phosphine is involved in the catalytic cycle. And again, we need a help from the DFT calculating to understand the energy difference in two transition states. Again, in this case, it's a non-covalent interaction play a key role in these reactions. The energy differences is about 2.5 kilocal per mole. It translated to about 95% EE. So in that sense, the DFT, theoretical or computational chemistry, does help us to understand the reaction mechanism, to explain our result more clearly. So I think my time is about up. So I just want to do a quick summary. I hope that you can agree with me through those examples that we are able to do the transition metal catalyzed selective KGBH functionalizations with almost all kinds of substituents that can be introduced into the cage boron or carbons, at a specific site. And then during that process, directing group play a key role in Regio selectivity. And the third point I want to say here, the transition metal catalyzed Enantio-selective functionalization of cluster can also be achieved, leading to the formation of a larger series of chiro at cage clusters. So you might ask, so why you want to make a chiro? Now you know the drug, chiro drug and non-chiro, they are very different. Because only one enantiomer is active, the other might be toxic. So in that sense, the chiro molecules or enantiomerically pure product is very important in the development of medicine. So the last point I want to make, we have made a huge amount of carborane derivatives, and then we expected that some of them might find applications in material medicine, organometallic chemistry, and more. So now in the SASTEC, we are doing translational chemistry. Basically, more specifically, it's carborane-based drug for neutron capture therapy. Yes. So I established my research group at CUHK in 1995. Now it's more than 30 years, 31 now. In the past 3 decades, so my chemistry focus on this cluster only, So at the early days, we are working on the organometallic chemistry by using those clusters as a ligand. So later on, we developed the functionalization method on the cage carbon and cage boron, and then we also do the supercluster chemistry, try to expand it, the size of the clusters, from the smaller one to the big one. So a number of years ago, I have shifted my research focus a bit from the pure fundamental chemistry to more applied, the translational research, working on the boron drug for boron neutron capture therapy. I think I have done nothing. All my student postdocs, so they have finished all the projects I have showing you today. So those are the past students, and those are the current students. They are with me at the moment. I have many collaborators from the Chinese U, from the Shanghai Institute of Organic Chemistry, from the SASTEC, and I also have received tremendous support from Professor Lin from HKUST and Professor Li Xueten from Hong Kong U in the development of those the boron drugs. And so here, Professor Xu Zhoufeng, actually he graduated from this department under the supervision of Professor Zhu. Okay? And the others who are in my group who are not working on this project, I didn't put their name here. And I like to thank the financial support. So you might wonder that Zheng Ping's name is not appear in my talk. See, actually, Zheng Ping spent about 2 years in my group as an IAP. He helped me a lot to develop a distinct research program from Carborane. So we have collaborated, we have co-authored about 7 papers in the 2 years. You can see he's a very productive guy and a very innovative guy. These are the 2 examples showing here. So when he joined my group as RIP, I tell him that you cannot do the carborane chemistry, right? Why? Because I tell him this RIP is a temporary position in my group. You have to develop something in boron chemistry, but not carborane. Right? Otherwise, you might have to find another job, right? Because RIP is a temporary. So then he came up quickly with a proposal to work on the diborane species. Okay, and this project, in fact, going very well. So we have more papers to be published in the diborane chemistry. So I thank him a lot for his kind of help during his stay in my group. Yeah, this is my current group. It's not very big, as you always expect. It might be a huge group. No, we are only about 20-something students and postdocs as well as our IAPs. Right now, some of you graduated. Now, welcome to contact me to join our teams. Okay, so welcome. So with that, I'd like to thank all of you for your kind attention and thank the selection committee for giving me this opportunity and thank Professor Zhu for hosting my lecture. Thank you so much.
Hey, thank you so much, Professor Xie, for the very nice talk. I'm sure everybody learned a lot from this perfect presentation. So now I would like to open the floor for questions.
Professor Xie, thank you for a nice talk. I have 2 questions. First, could you give a comment? I noticed for the enantio-selective synthesis, you almost all the ligand, they are monophosphine, right? Even though finally you have a bidentate phosphine, but you find just the one phosphine is functionized. So could you give a comment on this? Yeah, okay.
Yeah, okay, yeah, thank you. That at the beginning, so we screening all the phosphine-based ligand, nitrogen-based ligand, and then we also evaluate the phosphoric acid, and we even try some, box type nitrogen oxygen heterocycles, but somehow the screening result tells us that phosphine does well, in our case. But I have no clue about that. Yeah. So that's why we're screening all type of ligand.
Okay.
Yeah.
I mean the monophosphine compared to bidentate is because some like a steric, bulky, something reason to think.
Oh, there. the monodentate and the bidentate, that's probably we believe our cluster is quite a sterlic hindrance.
Oh, I see.
Okay, it occupy probably 1/3 of the space of the metal center already. Yeah.
Okay.
So in this case, the monophosphine is good.
Oh,
If the diphosphine, that's a two
corroded.
sterlic hindrance.
Okay, I
Yeah,
see.
only one binding site.
Okay.
Yeah.
I see.
If you both binding sites, like bisphosphines,
Yeah.
bonded to the metal, probably two bouquet for
Okay.
another coordination site.
Oh, okay, I see. Yeah, my
This is
sec-
just our, kind of explanation, but
Yeah, I
we do
see.
not have any concrete experiment.
Yeah, but I
with
think
that.
it's quite reasonable. Yeah, my second question is, you think the carborane that has some like properties like the benzene, but your first example shows you can install four floral atoms on the 4 positions. But in my opinion, for the like the benzene ring, if we add the first one, then the author and the pair positions already been deactivated, right? Yeah, for the benzene ring. But for the fourth, for your carborane, you install 1, 2, 3, 4. But it seems there's no influence for second, third, and fourth. Could you give some explanation?
Yeah, it's good
explanation?
questions.
Yeah.
Yeah, good questions. Because the benzene is a 2D molecule, right?
Yeah.
It's conjugated through the pi bond.
Yeah.
You know, pi bond, if you start from the beginning, the whole conjugate system will be affected through this electron configuration
Yes.
of the pi bond. In particular, in benzene, is a p orbital.
Yeah.
In the cluster case, you don't see any pi bond. You don't see, right? So this electron is delocalized over 2 electron 3-cent bond, or sigma bond.
Okay.
So we also call this molecule as a sigma aromaticity.
Oh.
So if one of these hydrogen is substituted by fluorine, only this BF bond, the polarity will change.
Okay.
The effect on the whole cluster is
I
minimal.
see.
So
yeah.
that's why you don't see those phenomena observed in the benzene.
Oh,
So
I see.
benzene is one substituted, the whole electron density of the whole molecule will be changed
I
because
see.
they are all
in the same
pi
plane.
bond.
Yes.
yeah pi bond like
Right.
it's kind of conductor,
Yeah. So
it can move electron very easily. Those are the sigma bond.
yeah, so it's
Yeah.
perpendicular to this plane. Yes.
Yes,
Yeah. Okay.
there's a difference.
Yeah, I see. Okay. Okay.
Right.
Thank you. Thank you.
Welcome.
Any other questions?
Yeah, Professor, a wonderful talk. Thank you very much. So I do have several questions. The first question actually just follow his question. So we have already put the fluorine on your boron cluster. So in this case, actually, this whole cluster should be the electron deficient. So did you try to use this as accepted to form the charge transfer with other donors?
Yeah, that's good questions. Again, because this is the sigma aromaticity. The substituents on the boron, the only mainly is so-called a localized effect. It has a very little effect on the charge density of the cluster. Yeah, based on the calculations. So the charge density of this boron, if this is fluorinated, and then change a lot, but the effect on the neighboring borons is very, very small, very little. Yeah. So you are right. The cage, by all means, is electron deficient because the boron is electron deficient. Yeah. The charge transfer materials based on the boron clusters has been reported or have been reported. Yeah. It can, for example, in certain case, the cluster can accept the charge. And then the cluster can also stabilize a different, it's called excited state as well. That's also been reported. Yeah. So this has been known, I will say.
Okay.
Yeah.
Thank you. The second question is actually, now you have already put a flooring on your boron cluster. So is it possible for us to put some pseudo halide, for example, like CN, to coupling and then attach on the other boron clusters or not?
Yeah, in principle, pseudo halide, like you can put the sulfur, selenium.
Right.
Well, you can also put the phosphorus,
Yeah.
isocyanide, cyanide. Yes.
Mm-hmm.
Yeah, that's no problem.
Okay.
Yeah.
So my third question is actually, when you do the catalytic coupling reaction, actually you need to choose the chiro ligand.
Yeah.
So it's possible for us to use a chiro solvent to induce this reaction. We don't need to use a chiro ligand to make the Kg have the quality.
Yeah, this is a very good, a novel approach, if possible. But to my understanding, so far I have not seen any examples by using chiro solvent for the asymmetric functionalization of any kind of molecules. So in principle, if you choose a right molecules, okay, and this is a ligand, can bind it to metal, okay, itself. So if this as a solvent, also as a ligand, this solvent can play a dual role in the reactions and might work. Yeah, only in the case it work. As on one side is a ligand, chiro ligand, on the other side is a solvent. If only the solvent, it can hardly realize. Yeah, because the coordination environment of the metal might not be changed if the solvent will not coordinate to the metal.
Any other questions?
Professor Xie, I have a question. Maybe it's not very correct. I see all the catalysts of mentor is expensive ones like iridium, high valent iridium, palladium. But I think recent days, and I think a lot of 3D mentor with a high oxidation state has been developed with strong field ligand. Maybe these 3D mentors like iron, cobalt, and manganese can be also applied as a catalyst for the ratio controlled catalyst for this pH bond activation.
Yeah, thank you for the questions. You are right. That's called a base metal catalysis. It's well known in organic chemistry. I haven't shown you the examples because I just shown you part of my research. In fact, we have developed the nickel copper iron catalyzed pH functionalization. We will publish about more than 10 papers, yeah, in this field. If you like to know more, you can check our website. We have put everything in the website. Yeah, no problem. Base metal can do, a very similar chemistry as the palladiums. And then today I also didn't show in, we're now able to do the electrochemistry. Yeah, electrocatalytic pH functionalization. Yeah, and then we also do a radical transformation. So we have metal, we can do the radical electron or just electrochemical base metal. Yeah, no problem. We also now, one work will come out by using manganese. Yeah, to do this catalyst, like group 2 metal based pH functionalization. It can also be done. Yeah. So I think there's a lot of chemistry need to be explored, though they might not appear in the field of pH functionalization. Yeah. I think as the field proceeds, many new results will be published. So I think last year we have published the granular version of the cluster. We're able to put a metal on this B, a magnesium. So this is just like a benzene, you know, granular reagent, right? And then we can put magnesium on the B side. So we make, we call nucleophilic clusters. So a reagent, once you have nucleophilic, then you can do a lot of things. So I think we published that in last, I don't remember exactly, but in Nature Communication. Yeah. So a lot of chemistry can do with the clusters.
Question?
So thank you, Professor, for your wonderful talk. So to follow his question, so for the fundamental research of carborane, so I can see that seeking for better way to do pH functionation, like as you said, using base metal, that's a good approach. And also for the chirochemistry, it's also very exciting. But other than this topic, what would be the future direction for the carborane chemistry?
Yeah, thank you. That's a very important question. Yeah, what we can do in this field, you can do further. So before I do the translational chemistry, in fact, I am not thought about that. So the chemistry, for example, we will ask ourselves, can you do the chemistry in water? Can you do the chemistry in the ultra low concentration? Because we now will do, we want to incorporate cluster into the peptide, into the small proteins. And in this case, we cannot run the reaction as usual in any of the organic solvent. Okay, we have to run the reaction in PBS or in water, pure water. So this is the question, so number one. Right? The second question, can you run, right now we run the reaction in millimole, right? Can we run the reaction in micromole? Very, very low concentration, because in the living system, you cannot concentrate it, the substrate too much. Can we do that? Okay. Then the third question, can we do the reaction selectively and in the 100% yield? Because we want to label the peptide or label the small protein with cluster. So those are the reactions, I will say, not in the chemistry. Chemists might not interest, but in the biology field, especially when you move a little bit, then we need to answer this question. And this is very tough, very difficult to achieve. So, but now we are working on that. Okay, we have to find a reaction, new reaction, to work in the pure water in the ultra low concentration, however, with excellent conversion and selectivity. Okay. So this is the direction we are working, and probably I will say this is probably the direction for this field.
Okay, thank you. So I have one last question, actually very simple, but actually I have this question for a long time. I've never asked you. So why do you choose O-carborane as a starting molecule? Because we know carborane have some other derivative like P-carborane and M-carborane. So why carborane, O-carborane?
Yeah, this is the main reason, because this is the most commercially available and then the cheapest one among the three isomers. Yeah. So this, at the beginning, this is the reason. So when I start this project as 30 years ago as an assistant professor, so with a limited support, you have to find something that's affordable. So, yeah. But now when we work on that, you look at that, the sterically or electronic, they are very similar. However, the biological activities are very, very different. That is a surprise to us. So we have prepared the O carborane, N carborane, the P carborane molecules, and then subject them to biological activity studies. The performance are very different. Yeah. In chemically, they are the same, no much difference. However, biological properties of these molecules or isomers are very different.
Since you mentioned the biological activity, I'm not sure if I can ask you something related to biology. So, could you please comment more on the application of carborane in medicine? For example, in BNCT, I guess, correct me if I'm wrong, you need to accumulate, concentrate those molecules in the tumor region, and I guess you need to functionalize with tumor targeting group, etc. So could you please comment more on that? Thank you.
Yeah, Guan, you are right. For the requirement for the BNCT boron drugs, we need non-toxic, number one. Number two, we need a highly concentrated boron inside the cell. The concentration means we need about at least 20 micrograms per cell inside this, the cell. The cell concentration is very, very high. Yeah. So number two, we need to deliver this boron inside the cell close to the nuclei as close as possible. So that in that case, of course, we need some transportation unit. So right now, we basically, because we need a large, or to transport a large amount of boron compound inside the cell. So we now are based on the amino acid, glucose, yeah, or basically we are now focusing on amino acids, sugars, as well as with some base, the base pair with install some base unit. Yeah, so that's currently we are doing.
Okay.
Yeah, we need, for example, antibody doesn't work in our case.
Okay.
Yeah, because it does not meet the concentration requirement. Although the selectivity is very high, it can targetedly deliver the species inside, to probably the surface of the cell. But we need to go inside the cell, go in. And also the antigen of the surface. I mean, it's not enough to reach a concentration to reach the boron concentration inside the cell. So the antibody doesn't work. Yeah.
Okay, thank you. Any other questions? If not, let's conclude our CTUHK distinguished seminar this afternoon, and please join me in thanking Professor Xie one more time for his wonderful talk. Thank you.
Thank you.